I am so happy for you guys today. You are getting to learn the chain rule. Now, before the chain rule, if we had something like this, we would not be able to find the derivative unless we put it to the fourth power first. An ick. Who wants to do that? So in this section, we are going to extend the differentiation formulas to include the composition of functions. So for example, let's consider this function, y equals 2x plus 3 to the power of 3. If we let f of u be u to the third, and let u be some function g, which is 2x to the third, then we can think of our original function as a composite function, where we can think of it as f of g of x, or f of 2x plus 3. Now, why? Why would we do that? Well, keep in mind, if I want to find the derivative of 2x plus 3 to the third power, what I would have to do is I would have to cube that thing out first and then take the derivative, which is going to take too long. So let's learn how to take the derivative of this. Now note, if we take this function, this 2x plus 3 cubed function, and think of it instead where u is equal to the 2x plus 3, and so we consider the u function, can we take the derivative of u to the 3? Yeah, u to the 3 is no problem. We take the 3, we bring it down, the u goes along for the ride, and then we reduce the power by 2. But when I take the derivative of u, I need to remember that u is defined in terms of x, right? U is this guy right here. So I can take the derivative using the rules that we've been learning, but I have to change some things around in order to compensate for taking the whole derivative. And this is called the chain rule. When we first get started, we're going to do the chain rule in this fashion. Okay, so for each function, they want us to find f of u and u equals g of x so that we can define it as a composite function. So notice they're not asking us to take the derivative yet. So for this function here, I'm going to say, okay, I want to define f of x as some function of some other function. So when I look at this function, I might say to myself, well, how can I write this function simpler? One thing I could do is I could say, all right, let's let u equal the inside of the square root. And then I can say, okay, so this creates this f of u where I'm really just looking at the square root of u. And I know how to take the derivative of the square root of u, right? I do. But again, don't worry, we're not going to do that yet. For this function over here, keep in mind that we know rules for the sign of plain Jane x to take the derivatives. So for this function, what I'm going to do is I'm going to let u be equal to the argument inside the sine function. So I'm going to let u equal 3x squared minus 5x. So I'm going to redefine this function as the sine of u. This is basically u substitution, where we take a complex function, like one of the original functions, and then we write it as a less complex function. Okay, same thing here. We start off with a complex function, and then we rewrite it so that it's still the same function, but it just looks less complex. And the big hint on this one often is let u be the inside of whatever it is. The inside of the square root, the inside of the sine function. Let u be the inside. So here's the definition for the chain rule. If I define my function as a composite function and both of these derivatives exist, then the derivative is equal to the derivative of the function times the derivative of the inside function. An easier form of the function is to think of it as f prime of u equals f prime of u times u prime, where u is equal to a chunk of algebra. Using Leibniz notation, where y is equal to f of u and u equals g of x, I can take the derivative by taking the derivative of the y function and then taking the derivative of the u function. And both of these cases work. So, for example, I have this function, the square root of x squared plus 5x. I need to find the derivative of f. And I'm going to use that first form of the chain rule. So that first form is where I'm looking at the inside of something, and I'm going to define that as u. So I'm going to let u be equal to the inside. I'm going to let it be equal to x squared plus 5x. So instead of f of x, I'm going to have f of u. And instead of having the square root of x squared plus 5x, I'm going to have the square root of u, which I can rewrite as u to the 1/2. Now I'm going to take the derivative of f of u. So the derivative of f of u is where I'm going to take this power 1/2 and I'm going to bring it down to the front. So I'm going to get 1/2 of u, and then I'm subtract 1 from that power. So I get 1/2 minus 1 is negative 1/2. And then I need to multiply that by the derivative of u, or u prime. Well, in order to plug that in to find my value of f prime of x, I'm going to need to substitute in the values I have back for that u. And remember that this thing right here, this is the regular u. And this thing right here, this is that u prime. Well, if I go back here, u is x squared plus 5x. But notice I didn't find u prime yet, so now I'm going to find u prime. So u prime is going to be, I'm going to take the derivative of this u function here. The derivative of the first term, I've got x squared. I'm going to bring 2 down, so I'm going to have 2x to the power of 1. The derivative of the second term, I've got a power of 1 on the x, and I'm going to do 1 times 5, and then reduce the power of x by 1, so I get 2x plus 5. And that's what I'm going to put down here. Next, I'm going to simplify. So I've got a fraction here, right? So this 1, this is going to go in the top part of the fraction. This 2, this is going to go in the bottom part of the fraction. These things right here, these are all going to go in the denominator because the exponent is negative. And instead of writing it to the 1/2 power, I'm just going to go ahead and put it back in root form. And then this next thing right here, the 2x plus 5, notice that there's no power on that, so that's just going to go in the top. And then the last thing I do is just simplify, and the only thing left to simplify is to just get rid of that 1. I don't need it. It is extraneous. And that's the derivative of my f of x. Cool, huh? So using the Leibniz notation, that's where we take the derivative with respect to x of that function of u, and then what we do is we get the derivative with respect to x of the function of u, but we also take the derivative of the inside, or the derivative of u with respect to x. So the first thing I'm going to do is I'm going to define the inside of the square root sign as u equals x squared plus 5x. And then I'm going to take the derivative of u with respect to x, and that's going to give me the derivative of this x squared plus 5x. So I've got 2x plus 5. All right, now I'm going to plug those things in. Now, if I take the derivative of this u function with respect to x, keep in mind that this is like saying that u to the 1/2. So this is like saying the derivative with respect to x of the u to the 1/2. So I'm going to take the derivative first here. So 1/2 u to the negative 1/2. And then this is the derivative of the inside, which we just write it like that. All right, well, let's substitute that stuff back in. So I need to substitute the u in. So I'm going to get here 1/2 times the x squared plus 5x to the negative 1/2. And then I'm going to put in the du dx. And that's where my 2x plus 5 goes. Again, make sure it's in parentheses because it's a binomial. And then I just put the top stuff in the top and the bottom stuff where it goes in the bottom. And that gives me my f prime of x. Let's do this next one. I want to find the derivative of f of x equals sine of 3x squared minus 5x. So once again, we can't just take the derivative of the whole thing. I need to use some u substitution. So I'm going to let u be equal to 3x squared minus 5x. And then since I know I'm going to use it, I'm just going to take the derivative of that real quickly. So the 2 comes down here with the 3, so 2 times 3 is 6. Reduce the power of x by 1, and I get 6x to the 1. For this next term, I'm going to take the derivative, have the power of x is 1 times negative 5, and then reduce the power of x by 1, and I end up with 6x minus 5. So now I've got my function, before I take the derivative, of f of u just becomes sine of u. Well, we know how to take the derivative of sine. So f prime of u ends up becoming, now what is the derivative of sine? Yeah, it's the cosine. And remember, the argument doesn't change, so I leave that u alone. But then I need to multiply it by u prime. Another way to think of this is if I am taking the derivative with respect to x of f of u, what I'm going to do is I'm going to take the derivative with respect to x of the sine of u. And the derivative of the sine is the cosine. But the derivative of u with respect to x isn't 1. So that du dx, that's that u prime. All right, well, let's go ahead and substitute it back in. So f prime of x is going to equal. So I'm going to take this cosine of u, and I'm going to plug in the stuff for u. And u, remember, was equal to 3x squared minus 5x. And then the next piece is I need to multiply it by u prime, or the derivative of u with respect to x, and that's this guy right here. So this is going to be times, and it's a binomial, so I'm going to put it in a set of parentheses, 6x minus 5. Now I can't simplify that anymore, although sometimes you'll notice that the answer key will often have the trig functions after the other types of functions, but honestly, that's not required. So now it's time for us to look at the old rules of derivatives that we learned in 3.1 and 3.2 and rewrite them with the chain rule. In other words, we're going to always let u be the differentiable function of x. Okay, another thing is, u is the inside of whatever. U is some chunk O algebra. If I've got the power rule, instead of, remember before, the power rule was where we were taking the derivative of x to the n, and we would get n times x to the n minus 1. Now, we still bring the power of n down. We leave the chunk of algebra alone, and then we take 1 less than the power, but now we're multiplying by the derivative of that chunk of algebra. And same thing here, just using the u prime notation. If I have the derivative of e to the u, where u is a chunk of algebra now, I'm going to do e to the u times the derivative of u with respect to x, or e to the u times u prime. Now keep in mind, and I had something before, remember if we would take the derivative with respect to x of e to the x, the answer was just e to the x. But what we weren't telling you is that it was actually e to the x times the derivative of x with respect to x. The reason why we weren't telling you that is because this is equal to 1. The derivative of plain Jane x is 1. So that's why you always just got e to the x. But now, if you have e to the u, and you've got some chunk of algebra in that exponent, the derivative is going to be e to the u times the derivative of the exponent. Our trig functions have been modified similarly. So instead of taking the derivative of sine of u, what we're doing is, instead of taking the derivative of sine of x, we're now taking the derivative of sine of u. And the derivative of the sine is the cosine. And then we multiply that by the derivative of the inside. Notice that we leave the u alone until the end. So the derivative of the tangent is going to be the secant squared of u. I don't touch the u. And then I'm going to multiply that by the derivative of the inside. And I'm going to replace all of these rules with similar rules. And just remember for future reference that du dx can also be written as u prime. So you may see me write it in that format. So let's do some examples. Remember, let's let u be the inside of the function. So think of this as u equals x cubed plus 5x. And u prime is going to be 3x squared plus 5. And so f of u is like saying this whole function to the 25th power. So this whole function to the 25th power. And if I take the derivative of f of u, what I'll do is I'll bring the 25 down in the front. I keep the power rule, I keep the u the same, and then I reduce this power of 25 by 1. And then I remember to multiply my answer by du dx, or my u prime. Okay, now that I've figured out what the derivative is, I'm going to write it back in x form. So f prime of x is going to be 25, and then I'm going to replace this u with what I use for the substitution. So x cubed plus 5x. And then next I need to multiply it by u prime, which I found to be 3x squared plus 5. Now sometimes you'll notice that your answers will be written with that 24th power at the end. But it's okay if you write it the other way. Just make sure you use parentheses when they're needed. I'm going to show you something different. It's basically the same thing, but it's just a different way to look at it. So sometimes I do take the derivative really without doing the u substitution. And when you get more comfortable with it, actually this is something that you can easily do. So when I take f prime of x, I think to myself, okay, this is like u to the 23rd, and I know how to take that derivative. Sorry, not 23rd, 25. So I take the power and I put it down. So I bring the 25 down. And then, just like I do for the power rule, I leave the inside alone. And then I reduce the power by 1. And then I multiply by the derivative of the inside. And then if I rewrite it, I get that answer. So once you become good at these, they're actually not too bad. Now, can I show you something that students do wrong all the time? Can I? Okay, good. I'm going to write this with a bunch of frowny faces and angry faces so that you know not to do this. This is a big time no-no. But often what I see people do when they take the derivative of something like this is they do this. They say, oh, okay, let's bring the 25 down. So they bring the 25 down. Then they take the derivative of the inside. Then they do the 3x squared plus 5. Then they reduce the power by 1. And then they think they're done, and they are, but they also just got the problem totally wrong. So don't do the stuff in red. Definitely do the other stuff. All right, let's try another example. Ooh. All right, this one's pretty cool. First of all, it's cool because it uses the product rule. Second of all, I am going to rewrite this because I want to be able to take the derivative easier. Okay? All right. So this function here for the product rule, think of this as f, and this is g. So if you're going to do y prime, you need to do the first times the derivative of the second plus the derivative of the first times the second. So for y prime, I'm going to write down the first function, which is x, and then I'm going to take the derivative with respect to x of the sine of x to the negative 1. And then I'm going to add to that, because it's product and plus, the derivative of the first, which is going to be the derivative with respect to x of x, times that second function. And now I'm going to simplify. Okay, this x goes along for the ride. This thing right here, if I take the derivative of the sine of x to the negative 1, remember, what's the derivative of the sine? Good. It's the cosine. Don't you dare touch that x to the negative 1. Remember, we don't touch it yet. Now is when we touch it. Now we're going to take the derivative with respect to x of x to the negative 1. So this whole thing here, that's from the derivative of the sine of x. And now I get to my plus. The derivative of x with respect to x, no problemo. That's 1. Super easy. And then this sine function, and we didn't do anything with it. We're just going to write it down. Okie dokie. So x drops down. The cosine of x to the negative 1 drops down. And then this derivative, I'm going to take the negative 1 and I'm going to bring it down. And I'm going to have negative 1 times x to the negative 2. And then I'm done because I did it with x and I'm doing it with respect to x because as we know, the derivative of x with respect to x is equal to 1. Now I'm moving on to the plus. 1 times sine is just going to give me sine. And then pretty much at this point, I'm done. I'm just going to rewrite things. So y prime is going to give me, I'm going to write down the stuff I have. So x cosine of x cosine, of 1 over x. And then notice there's this negative sign right here, so I'm going to put that in the numerator. And then x to the negative 2 means that x squared is in the denominator. And then the plus comes down, and then sine of 1 over x. And then that's my final answer. For this next one, because this is like chain rule in chain rule, is I would rewrite the cosine function as a power rule, like that, until you get comfortable as thinking about it as the power rule. Now, I'd like to point out that if you're going to do the chain rule twice, it's better to use different variables. So I'm going to use u, which is the inside, but then I am also going to use w, which is the inside of the inside. So I'm going to rewrite this cosine as the cosine of w. And then I'm going to take u prime, or the derivative of u, with respect to x. And the derivative of cosine is the negative sign. But then I also have my y, or my w prime, because it's not just the sine of x. And then my w prime here, if w is 7x, my w prime is 7. So we're going to think about it as u to the 4. Okay, we're going to think of it as u to the 4. And then remember, when I take the derivative of u to the 4, what am I going to get? 4 times u, reduce the power by 1, and then multiply it by u prime. Well, let's do that. So let's substitute it back in. So now I've got it for my x's. So here's my 4. My u to the power of 3 is going to be my cosine of 7x to the power of 3. And my u prime is this thing right here. It's that negative sine of w times w prime. But remember that w is 7x. And that w prime is 7. So what I end up getting for y prime is, and if I combine my stuff here, I've got a negative and I've got a 4. So I'm going to put a negative 4 in the front. And then I'm going to do my lower, oh, darn it, I forgot the 7. I got a negative, a 4, and a 7, so this really is negative 28. And then I'm going to put my lower power function first because I'm multiplying stuff here. And then I'm going to put my higher power thing after. And I can write this with parentheses for the 3, or I can just put the 3 back in between the cosine and the argument. Remember from previously, if I have a trig function to a power, it goes between the trig function and the argument, or we write it in parentheses. Those are the two ways. All right, I know this seems like a lot, but trust me, you can do it. I'm going to show it again. just because I think I like to do things multiple times. Okay, so keep in mind, I am going to take the derivative, so I'm going to show it kind of like with the shortcut, because sometimes although that variable substitution can get a little hinky, also sometimes students like to see it a different way. All right, so the first thing I'm going to do is I'm going to think about this as multiple stepped. So I've got, let me color code some things. Here, first of all, I've got the power of 4, right? And that power of 4 is dealing with the inside, which is the cosine of something. And then inside that cosine is the 7x. All right, so now I'm going to take that derivative. So when I take the derivative, I basically am starting from the outside and working my way in, kind of like peeling an onion. So I start with the power of 4 and I bring it down in front. And then remember, the inside stays the same and I reduce the power by 1. So the inside just becomes nothing. Why did I? It's not worded right. I'm sorry. I'm thinking about something else. A fly just flew in front of my face. The inside is left alone. It stays the same. We haven't changed it. However, I have to take the derivative of the inside. So now I'm going to take the derivative of the cosine. And the derivative of the cosine is negative sine. But the inside goes along for the ride. And now I take the derivative of the last inside. And that is 7. And notice if I put all of that together, I get this handsome little devil right there. Oh my gosh, this problem. I forgot I had this one in here. You guys are so lucky. All right, I'm going to color code this too. So let's just take a moment to appreciate the complexity of this particular problem. This particular problem has not only the product rule in it, but this thing also has power rule. See those powers there? And it has chain rule. It's a fabulous problem. All right. Ready to keep your wits about you? Good. Okay, let's do this. So, y prime. Remember, let me just rewrite this real quick. The product rule. Okay. All right, so product rule. I'm going to take my first function and I'm not changing it at all. I'm not taking the derivative, nothing. And then next, I'm going to take the derivative of this bad boy. Notice what I'm doing. I'm not taking the derivative. I'm writing out my game plan. Next, because product is plus, I'm going to write down the derivative of my first function. And my first function is that 2x plus 1 to the 5th. And then I'm going to multiply that by my second function, which I'm not changing at all. And that's going to be to the 4th power. Okay, so let me just take a moment to kind of color code it so you can see what happens. Here's my first function. There's f. Here's my derivative of the first function. Okay, so here's f and f prime. And then here's the derivative of my second function and then my second function. So here's g prime and g. All right, ready to tackle this baby? English language is so interesting, so many colloquialisms that we have. Are you ready to tackle this baby? Who tackles babies? Okay, 4 comes down in the front. So I get x cubed minus x plus 1 to the power of 3. But I'm not done because I got to take the derivative of this inside. Now I'm moving on to the plus. Now I'm going to take the derivative of this function. I'm going to take this 5 and bring the power down to the front. So 5, 2x plus 1 to the power of 4. And then I'm going to multiply that by the derivative of the inside. And then remember, this last one here, this didn't change at all. So there's nothing going on there. I'm just multiplying. All right. For this last one, what I'm going to do is I'm going to take these last derivatives. Notice that these are the last line of derivatives I'm going to take before I do some simplifying. And believe it or not, there's a ton of simplifying. I'm going to simplify a little bit first. I've got this 4 here. I'm going to bring that to the front. And then I'm just going to do the 2x plus 1 to the 5th. And the x cubed minus x plus 1 to the 3rd. And then I'm going to take this derivative here. So this is going to be 3x squared minus 1. And now I move on to the plus. See how the plus carries down? All right, here I'm going to clean some stuff up. I'm just going to write the 5, the 2x plus 1 to the 4. So that's me writing this stuff here. And then I'm going to skip over the derivative because I'm going to do it a second. And I'm just going to write this other piece here. X cubed minus x plus 1 to the 4th. And now I'm going to write this derivative down. And the derivative of 2x plus 1 is just 2. Super cool, right? Well, if I look at this function here, notice that this is a 10, right? Okay. All right. However, let's simplify, because why would we leave it like this? We've got a few more steps. So what I'm going to do is I'm going to go through and I'm going to identify some common factors. So between 4 and 2, I can take a 2 out. Between 2x plus 1 to the 5 and 2x plus 1 to the 4th, I can take out 2x plus 1 to the 4th. From the x cubed minus x plus 1 to the 3rd, and the x cubed minus x plus 1 to the 4th, I can take out the 3rd power. And from this, I can't take anything out. I'm stuck with it. And same with this 5, I'm stuck with that. All right, so let's write what I have left. Okay, 4 divided by 2, that's going to give me 2. Here I've got 2x plus 1 to the 5, and I took out 2x plus 1 to the 4, so I'm going to be left with 1 power of 2x plus 1. Here I had this guy to the 3, and I'm taking out this guy to the 3, so poof, disappear. And then remember, I didn't get to get rid of this one, so the 3x squared minus 1 was down for the ride. And oh my gosh, it took me a while, but I got to the plus. Next, 5 divided by 2, I can't do that, but here I got my 2 divided by 2, perfect. That's gone, the 5 stays. Next, 2x plus 1 to the 4th, and I'm dividing out 2x plus 1 to the 4th, so poof, disappear. None of those come down. And then x cubed minus x plus 1 to the 4th, I took out a power of 3 of that, so I have a power of 1 of that left behind. I know that's a lot, but just rewind it and watch it again if you're confused. This is maybe the good thing about COVID, that all the lectures are online. But just understand basically what I did, and I'm going to go up here to the top, is I had this like convoluted function of like x to the 5, y to the 2, plus x to the 6, y. And what I did was I took out the common factors, right? So that's essentially what I did. Okie dokie. I'm sure you wanted to hear this, but there's more work to do to simplify this. So I'm going to cheat a little bit because I'm kind of running out of room at the bottom of the screen here. But I'm going to multiply this out. So I'm going to multiply this 5 out. So I've got 5x cubed minus 5x plus 5. And this little stinker right here, I've got to multiply this out. So I'm going to get 6x cubed times 2 is going to give me 12x cubed. So 6x cubed times 2, yep. 2x times negative 1 times 2 is negative 4x. And then 1 times 3x cubed times 2 is, 6x squared. I said cubed, I meant squared. And 1 times negative 1 is negative 1 times 2 is negative 2. All right, sorry for doing that quickly, but again, space. Basically what I did was I multiplied these 3 together. And I didn't have like terms. So, all right. Let's go ahead and combine these guys. Okay. This stuff in the front just goes down along for the ride. And I'm going to combine the stuff in the purple. All right, 12x cubed and 5, it's a plus 5x cubed. That's going to give me 17x cubed. And then negative 4x and negative 5x is going to give me 9x, but I don't want to forget I've got a positive 6x squared there. So I combined these guys first, then I wrote this guy down. Now I'm going to combine the x's. And then I'm going to combine my numbers. Now the last thing I need to do is just make sure, can I factor anything out of that now that I've combined all the like terms? And I can't take the same number or number of letters out of these. So yeah, I'm good. Hokey Pete. What a good problem, huh? I would also look to see if maybe I could factor that by grouping, but again, I couldn't. I wouldn't be able to. All right. That's a long one. It's a good one, but it's a long one. Watch it again if you need to. Make sure you understand all the little nuances of this problem. So we already know the derivative rules for e to the u. We know that the e to the u just goes along for the ride, and then we take the derivative of u with respect to x. But what if we have this a to the x, okay? So where a is not equal to e. Well, let's do some stuff, okay? So let's let a be equal to e times the natural log of a. And that's just basically saying like a equals a plus 1 minus 1. Yeah, we know that's true, right? But we're just doing it with exponential and logarithmic speak because we're champions and we got mad street cred when it comes to our math skills. All right, so now if we have this y equals a to the x, I could rewrite this y equals a to the x as y equals e times the natural log of a to the power of x. which is just e natural log of a times x, because a power to a power multiplies, right? All right, now we're going to take the derivative. So we're going to say, okay, let's take y prime, which is going to give me the derivative with respect to x of e to the natural log of a times x, which, and as we know, the derivative of e to the x is e to the x, or e to the u is e to the u prime. So this derivative is going to be e to the natural log of a times x times the derivative with respect to x of the natural log of a times x. So this thing right here, e natural log of a times x, as we know, is just saying a to the x. But just in case you didn't remember that, let's just rewrite this in this way. But this derivative function right here, like if I took the derivative of 2x, I'd get 2, right? Well, natural log of a is just a number. So the derivative of natural log of a times x is just natural log of a. So then let's simplify. So y prime equals, remember our substitution from the beginning, this thing right here equals a. And then we've got a to the x, and then times natural log of a. So now we've got this formula. So y prime equals a to the x times natural log of a. So let's write this for u. So if I'm taking the derivative of a to the u, and let me just write above it, remember the derivative of e to the u is e to the u times u prime. But the derivative of a to the u is going to be a to the u times the natural log of a times u prime. Okay. What we're missing is the natural log of a when we have a different base than e. Now, this should make a little bit of sense because, like, what's the natural log of e? Yeah, that's 1. If you don't believe me, plug it into your calculator. See what it gives you. Okay, let's find the derivative. So, y prime. Derivative of x squared is going to be 2x. Ah, the good old days. Next, let's take the derivative of 2 to the x. So the derivative of 2 to the x is, remember the formula, the derivative of a to the u is a to the u times natural log of a. So it's going to be 2 to the x times the natural log of the base, which was 2, and then times u prime. So times the derivative with respect to x of x, because that's what my exponent was. And then I'm just going to simplify my stuff. 2x plus, here I've got 2 to the x times the natural log of 2 times the derivative with respect to x of x is 1. So I'm done. Super exciting, huh? Let's take a look at this next problem. Now, much like a lot of the exponential problems, we're just thinking slightly outside of the box. They're saying for what values of r does the function y equals e to the power of rx satisfy this differential equation of y double prime minus y prime minus 6y equals 0? Well, let's figure that out. First, we know that y is equal e to the power of rx. Now r, because they're saying what values of r, so r is like a constant, okay? It's a value. Weird, I know, but it'll be okay. We'll do it. We can do it. All right, now we've got to take the first derivative. The derivative of e to the u is e to the u times u prime. So I'm just going to rewrite that. I'm going to put the r first. All right, now y double prime. So this r goes along for the ride. And then the derivative of e to the u is e to the u times u prime, which I'm going to rewrite that too. And I could go on forever and ever, amen, because this is fun, but I only need y double prime and y prime for this function. So I'm going to use these to plug it into my function of y prime, double prime minus y prime minus 6y equals 0. So let's plug some stuff in, man. So y double prime, that's this guy, r squared e to the rx, and then minus y prime, that's this guy, r e to the rx, minus, and then 6y, y is this one, so it's going to be 6 times e to the rx equals 0. Okay, so now we need to figure out what values of r make this 0. Right? You ready to solve that? You know how to solve that, right? I know it looks really intense, but how about I recommend something? Let me try something. What if I factored out e to the rx out of all of those terms? What would I get? What would I get? Yeah, go ahead and factor it. I've got faith in you. You can do it. Yeah, look at that. Look at that. Look at that. Do you know what that is? Well, the first part's a linear, but the second part's a quadratic. And we know how to solve a quadratic. We just set it equal to 0 and solve for the variable. So okie dokie. All right, now we're looking for all the values of r that make this equal 0. So I'm going to take r squared minus r minus 6 equals 0. And then I'm going to take this e to the r times x equals 0. In this one right here, nope, that doesn't happen. Exponential function doesn't equal 0 unless I'm plus or minusing something. So no. But this other one does. R squared minus r minus 6. Yeah, that bad boy factors. What factors of 6? Subtract to give me negative 1. Did you say negative 3 and 2? Oh my God. I'm so impressed. Good. Yeah, those are my answers. R is equal to 3 or R equals negative 2. Those are the values of r that satisfy this hefty equation here. Neat, huh? This is a good one to do at parties. Yeah. You make lots of friends. I mean, a lot of friends. And actually, never mind. It's probably not a good idea during COVID. Okay. That's the chain rule and a little bit of some logarithmic, well, not logarithmic, sorry, a little bit of exponential functions. I hope you enjoyed that lecture. If you didn't, go take a walk around the block and scream into a room in a pillow and then watch it again. And I bet it'll go better. Okay, guys, see you in a bit. I have faith in you. You can do it.